Today we are going to study and understand the complete coordinate system used in construction field, particularly in road construction. Today we will go through 1. Understanding the basic coordinate system by using Pythagoras Theorem and simple trigonometry. 2. Understanding the northing and easting system. 3. Fixing of coordinates by theodolite and disto-meters. 4. Fixing the coordinates by using total station. 5. Detailed study about GPS system and his usage. It is explained in a simple and easy way to understand. We will learn everything just in 15 minutes time. Welcome to Civil Guru. Our videos are available in different languages such as English, Spanish, French, Arabic, Hindi and Tamil. Please select your desired language from our playlist or the links given in the description. If you find this video helpful, hit the like button, subscribe, and share with your friends. Thank you. Let us understand the basic coordinate system. Imagine you are standing in an open field and you want to describe your exact location. How would you do it? This is where the coordinate system helps. Let us create a XY coordinate system. Think of a simple graph with an x-axis, left to right, and a y-axis, up and down. Any point on this graph has a unique location, written as x, y. Now let us calculate the distance between two coordinates by using Pythagoras Theorem. The formula of Pythagoras Theorem, distance c equals square root of a square plus b square. The same formula we can use it as r equals square root of x square plus y square. Here the r denotes the polar distance between two coordinates. Let us assume two coordinates a and b. The coordinates of point A equals 2, 3, that is x1, y1. The coordinates of point B equals 5, 7, that is x2, y2. Now, x equals x squared minus x1, that is 5 minus 2, that means x equals 3. Similarly, y equals y2 minus y1, that is 7 minus 3, that means y equals 4. Now the distance between point A and B equals square root of 3 square plus 4 squares. That is square root of 9 plus 16. That is square root of 25. That is 5. Means the polar distance between point A and B is 5. Now let us find the angle between these two coordinates by using trigonometry equations. Tan theta equals opposite side by adjacent side. So theta equals tan inverse of opposite side by adjacent side. Now, in our case, the opposite side is y value, that is 4, and the adjacent side is x value, that is 3. So 4 by 3 equals 1.333. Now theta equals tan inverse of 1.333. Finally, the theta equals 53 degrees 7 minutes 23 seconds. This formula helps surveyors find the direction or bearing of one point from another. There are some situations, the surveyors get the angle and distance of any new points from known points. In this situation, we shall know how to get the coordinates from the available information. Here in this graph, assume we have the distance as 5 between two coordinates, and the angle between 2 points is 53 degrees 7 minutes 23 seconds. Now let us see how to get the coordinates. Using trigonometry for angles. Sin theta equals opposite side by hypotenuse. So, opposite side equals sin theta times hypotenuse. In our case, the information available, theta equals 53 degrees 7 minutes 23 seconds, and hypotenuse is distance between 2 points, that is 5, and we have to calculate the opposite side, that is vertical height, that is y. So the value of y equals sin 53 degrees 7 minutes 23 seconds times 5. The value of y equals 4. Similarly, to find the adjacent side value, that is x value, let us use the cosine. Cos theta equals adjacent side by hypotenuse. So, the adjacent side value, that is x equals cos 53 degrees 7 minutes 23 seconds times 5. The value of x equals 3.000. The coordinates of point A equals 2, 3. The coordinates of point B, x2 equals 2 plus 3, that is 5, and y2 equals 3 plus 4, that is 7. Finally, the coordinates of point B equal 5, 7. Now that we understand coordinates, let's see how surveyors measure them in the real world. Understanding northing and easting in surveying and its applications. In real-world land surveys, we don't just use X and Y coordinates. Instead, we use a special system called northing and easting to define locations on the Earth's surface. It is also called as latitude and departure. Northing and easting coordinates are crucial in land surveying, engineering, and mapping. They are widely used in computer-aided design (CAD) software, town planning departments, and topographic surveys. Here we will explore following aspect in detail. What are northing and easting? How northing and easting work in CAD and GIS. Importance in town planning. Application in topographic surveys. Instruments used for northing and easting measurements. What is northing and easting? Few years back, before GPS get familiar, this northing and easting widely used in land surveying. Northing and easting are coordinate values used in a grid-based system to specify locations on the Earth's surface. Easting, that is X coordinate, are used to measure distance east or west from a reference point. Generally, it is from meridian. Northing, that is Y coordinate, are used to measure distance north or south from a reference point. It may be from equator or generally from a baseline used for every project. These values are typically measured in meters and are part of the Universal Transverse Mercator or state plane coordinate system. How is it used in road surveys? Every survey point has a unique easting-northing value. This helps engineers accurately plot roads, buildings, and land boundaries. Suppose a surveyor marks 2 points. Point A easting equals 5,000, northing equals 3,000. Point B easting equals 5,500, northing equals 3,200. The difference helps calculate distance and angle between 2 points as we have covered in previous chapter few minutes back. These type of measurements underpin urban planning efforts, allowing for effective land use and infrastructure development. The theodolite and chain or disto-meter. Long before modern instruments, surveyors used a simple method, the theodolite and measuring chain. Let's see how. The theodolite, a tool used to measure angles precisely in surveying. It has a telescope that rotates to sight different points. The survey team would stretch a metal chain between 2 points and record the distance. Using the theodolite's angle reading, they would calculate coordinates manually. Later, the technology improvement helped to find the disto-meter, a laser distance meter. Instead of a physical chain, we used this laser distance meter, which is known as disto-meter. It sends a laser beam to a target and instantly measures the exact distance. But even with a theodolite, surveyors had to do manual calculations. What if we could automate this? That's where the total station comes in. Total station with EDM. Now, meet the total station, a high-tech survey instrument that changed everything. What is a total station? It is a combination of a theodolite plus EDM, electronic distance meter, plus computer. It can automatically calculate coordinates and store them digitally. Now let us see how it works. The surveyor sets up the total station on a known point. It measures the angle and distance to another point. Using built-in formulas, it instantly calculates the new point's easting and northing coordinates. Also, It helps to record the field information and import in CAD, that is Computer-Aided Designing, or GIS, that is Geographic Information Systems. It helps a lot in urban planning and land development and public works department for planning and designing. By adding Z coordinates with northing and easting, it helps to create the topographical survey. This made surveying much faster and more accurate, but even the total station has a limitation. It needs a clear line of sight. What if we need to survey over mountains, forests, or water? That's where GPS comes in. Now, we enter the world of satellites. GPS, Global Positioning System, allows us to measure coordinates anywhere on Earth without needing to see the point directly. But how does it work? How GPS works? It is the power of 24 satellites. GPS is a network of 24 satellites orbiting the Earth at a height of 20,200 kilometers, which is 12,550 miles. These satellites are constantly moving and are positioned so that at least 4 satellites are visible from anywhere on Earth at any time. Each satellite continuously transmits radio signals containing the satellite's location and the exact time. The concept of trilateration. Now, imagine you are standing in a park with a GPS receiver. How does it pinpoint your location? Step 1. The GPS receiver picks up signals from at least 3 satellites. Step 2. It measures the time delay of each signal to calculate the distance from each satellite. Step 3. Using a mathematical process called trilateration, it determines your exact position in terms of latitude, longitude, and elevation. Example period. Suppose you receive signals from DOT. Satellite A, 20,000 kilometers away. Satellite B, 21,000 kilometers away. Satellite C, 19,500 kilometers away. The receiver calculates where these 3 distances intersect, giving you an accurate location. But wait, if 3 satellites give us a location, why do we need a 4th one? Why do we use 4 satellites? The 4th satellite helps correct errors caused by atmospheric interference and clock inaccuracies. This improves accuracy from a few meters to centimeters depending on the GPS type. Now let us see the types of GPS used in surveying. Now that we understand how GPS works, let's explore the different types used in surveying. Type 1. Standard GPS, handheld. The accuracy of this type is 1 to 5 meters. This is used in mapping, navigation, and general positioning. Type 2. Differential GPS, DGPS. The accuracy of this type is 10 centimeters to 1 meter. This type uses ground-based reference stations to improve accuracy. This type is used in land surveying, agriculture, and marine navigation. Type 3. RTK GPS, real-time kinematic GPS. The accuracy of this type of GPS is 1 to 2 centimeters. This also uses a base station and real-time data corrections. This type is majorly used in road construction, precision engineering, and high-accuracy surveys. Now the question arises, what is ground-based stations in the GPS system and how they work? The Global Positioning System, GPS, relies on a network of satellites, ground-based control stations, and user receivers to provide accurate location data. Ground-based stations, also known as GPS control stations or reference stations, play a crucial role in maintaining the accuracy and reliability of the system. Ground-based stations are fixed locations on Earth that monitor GPS satellites to ensure they are functioning correctly, correct errors in satellite signals caused by atmospheric conditions, improve accuracy by providing real-time adjustments. These stations are part of the Global Navigation Satellite System, GNSS control segment, and are managed by organizations like NASA, the U.S. Department of Defense, and space agencies worldwide. In real life, it helps in surveying and navigation system. The surveyors use ground station corrected GPS to map land with centimeter level accuracy. The self-driving cars rely on corrected GPS signals to navigate safely. The ships use DGPS stations for precise docking and marine navigation. From simple measuring chains to high-tech GPS, surveying has come a long way. Today, every road, bridge, and building relies on these tools for precise placement. Next time you drive on a highway or see a construction site, you'll know the science behind it. If you enjoy this video, subscribe now and share with your friends. Also, don't forget to press the bell button. Thank you.